Hello. So today there's an additional way to take an attendance in addition to the sign-in sheet floating in the room, your clicker responses. This. You hear, your exam is gone. If your exam still's here, you didn't come. So please take a look at the picture, question, answers, prepare your clicker, and choose the answer of your choice. The grades for the homework for the exam, the grades have been posted on Blackboard. And the first thing to do is to check if the grade you see on Blackboard is the same as the grade you read here. Because when people enter your grades into the Excel file, sometimes they just make a mistake. It happened once or twice in the past. So to ensure your grade is correct, you should check and compare. If the grade on the Blackboard is lower than this one, you should tell me. Otherwise, it's up to you. See how many people are missing, and they all have entered here 0 missing lectures. Interesting. Another fact. I'm collecting a lot of information. Six, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 20, 5, 6. I want to, again, thank you for your feedbacks. I haven't read them too many yet. I'm going to do it over the weekend. And I'm going to probably just post it on a Blackboard as well, so anybody could print it out and fill it up if you still have any suggestions to make. Okay, it's changing. Well, I'm going to probably give you an opportunity to answer this question one more time. Let's see, so number 2. Got it? B, 0, C, positive. Almost 50-50 distribution between these two answers. So when the ball is moving down or up, and we look at the force of tension and its instantaneous velocity, which basically it's instantaneous displacement over instantaneous time. What we see is the angle of 90 degrees between the force. It's too early for that. So the tension always points along the string, and the velocity always tangent to the trajectory. So at any location of the ball, these two vectors, the force of tension and instantaneous velocity, instantaneous displacement divided by instantaneous time, are perpendicular to each other. So this angle is always equal to 90 degrees. And we are calculating the work of that particular force. So now I'm going to limit the time. Of course, this is the equilibrium position, and right now this ball has no kinetic energy. Potential energy depends on our choice, but normally we choose the origin at the lowest location. So if the origin is here, the potential energy is also zero, and mechanical energy equals kinetic plus potential, zero. So if I do some work, now my hand does work, yeah? The work done by my hand getting transferred into the potential energy of this ball. So if I release it, the potential energy will be decreasing, but it's going to be moving faster and faster. So kinetic energy will be increasing. Neglecting friction, mechanical energy is supposed to be conserved unless there is some kind of another non-conservative force acting on it. Can't wait to see what you think again. See, the distribution is different. Now, the majority tells us that it has to be equal to zero. The second answer was zero, and it is. Because as we know, if we calculate the work done by a force, if the angle equals 90 degrees, cosine of 90 equals zero, you multiply by anything, it's going to be zero anyway. Even if the force, generally speaking, change, still the angle remains the constant. The angle remains equal to be 90 degrees. So the conclusion is simple. It doesn't do any work. The tension force, like normal force, doesn't do any work because of the angle. So that's the second force, which is acting but doesn't do any work. So the only work being done in this situation is by force of gravity, because only two forces acting on it, tension and gravity. Tension doesn't do work, so only gravity does. And for any two locations of this ball, any, we can write, well, we always have two choices, remember. The choice number one, work kinetic energy theorem, or the choice number two, the law of conservation of mechanical energy, which are equivalent to each other. But this is more convenient when friction is involved. This is more convenient to use when there is no friction, no non-conservative forces. So like in this case, we don't have any non-conservative forces. We can apply the law of conservation of mechanical energy. mv initial squared over 2 plus mg, well, y initial, h initial, doesn't matter, should be equal to mv final squared over 2 plus mgy final. Now, in this particular problem, we should relate this location and the location when the ball stops, reaching maximum height. So, well, that location is somewhere. Well, I could have asked, what do you think with this in this case? The final location is below this red line, exactly at this red line, or above? Well, again, if we just release it from rest, because mechanical energy stays conserved, it can't go any higher. That would increase mechanical energy. So if we release the ball from rest on the opposite side, neglecting friction, it reaches exactly the same height. But that's not the case. In this situation, we actually supply some additional kinetic energy first. So what should happen? Well, not exactly like that. If too much energy, but something like this. Yeah. So it stops above the initial level. So in this situation, the final position is over here. But what is important, it stops before it starts moving back. So if it stops, what does it tell us? And you see, you have to keep in mind the treasure map of what is connected to what. Final velocity or initial velocity connected to what? Well, in general, they have many, many connections. Displacement, acceleration, time. Those are direct connections. But there is one more direct connection, which is kind of more reasonable to mention when we talk about energy and work. Velocity is related to what? Kinetic energy. Kinetic energy. So this is the link which we have to exploit in this problem. So if final velocity is 0, that means kinetic energy is 0. Now, relative to the ground, of course, we have no information about the initial height and final height, but that doesn't matter, right? We don't care. We know that it's 20 centimeters higher. So we know that this is supposed to be equal to 20 centimeters or 0.2 of a meter. So because we choose the 0 level, we can choose it here. Again, at the lowest position, which now is the initial one. So that makes this equal to 0. And there is no indication about how heavy it is, but it doesn't matter because, as we can see, mass canceled. So we can solve it for the initial speed immediately. 2 times g times this and square root of that. A number that's supposed to be 2 times 10 times 0.2 equals 2 square root of 4, 2 meters per second. So the initial speed of this ball was equal to 2 meters per second. And it doesn't matter if it's a very heavy or very light ball. If its initial speed is 2 meters per second, on another side, it's going to be 20 centimeters higher. That's it. That works for many, many situations involving gravity. You see this, if you remember, this equation is exactly the same as for the, well, regular ball falling down. It's because tension doesn't do any work, so only gravity matters. So all problems related to free fall can be solved exactly like that. We don't have to use motion equation or velocity equation. We can use the law of conservation of mechanical energy. Any questions? So this slide just gives examples of several equations for several pairs. We always have to write a pair, have to choose a pair of positions, because conservation means stays the same. Something now is the same as something after. The position number 1, the position number 2 should be related. A roller coaster. What is the difference between the ball on a string and a roller coaster? There is no difference. Normal force is always perpendicular. So in the absence of friction, normal force doesn't matter at all. So if we said neglect the friction, that means, well, the work done only by gravity. In that case, again, the most convenient approach is using the law of conservation of mechanical energy. If there is no friction, the law of conservation of mechanical energy usually gives the answer faster. So I choose 0 here because I'm looking for this speed. And in that situation, my y initial will be equal to 20. Y initial is 20. Y final is 0 because of my choice. V initial equals 0. V final equals question mark. So mv initial squared over 2 plus mgy initial is equal to mv final squared over 2 plus mgy final. You see, the law is exactly the same. Exactly. So now, this is 0. It starts from rest. This is 0. Because of our choice. And again, m getting cancelled, so 10 times 20 should be equal to final speed squared divided by 2. Final speed is equal to square root of 10 times 20 times 2, 20. And by now, I hope the majority of people who spend considerable amount of time in this room understand that this is 5 and this is S. I don't know. Moving on. So, of course, the approach doesn't matter on the direction of the motion. Could be moving from higher position to the lower. In this problem, it's moving from a lower position to the higher. But in this problem, we also have to consider the presence of the force of friction. So in this situation, I wouldn't use the law of conservation of mechanical energy. I would use the work kinetic energy theorem. If this is a 3, 4, 5 ramp, we can consider meters here. Anyone, please tell me what is the angle of the incline? I don't have many slides. I just have to kill time. So that's not true. I'm kidding. I have a lot of slides. Of course, we did it many, many times. So now we give a push. So the initial speed is not 0. And we are looking for that minimum speed we have to supply it so it would reach the top of the ramp. If the speed is less than that, it stops before reaching the top. If it's greater than that, it just falls over, flies away. So it stops at the very edge of this ramp, which means final speed equals someone should say something. 0, of course. If I stop talking, that means I'm waiting for something to happen. Again, it's how many weeks you should kind of get an idea how it works, right? So if we write the work kinetic energy theorem, kinetic energy final minus kinetic energy initial should be equal to the total work done by all the forces. And the final kinetic energy, of course, is 0 because it stops. And the initial kinetic energy equals mv squared over 2. That's an unknown which we're looking for. So now we just have to step by step write the expression for work of each individual force done on this box. And what we have is gravity, normal, kinetic friction, and because we did a push, we gave a push, there's some kind of a pushing force. Yes, my free body diagram is exactly the same. No, my free body diagram is different. Actually, before I have to, did I take a picture of that? Just in case. Now we can close it, cover. Come on. And now I can start collecting your answers. And now I'm going to turn on the timer. Come on. It changes so fast. Time fly. Nice. Well, maybe there's a student or two who get the grade in the final, or I mean, on the last exam, maybe just a point higher than they deserve. Because this is a wrong diagram. You can't solve this problem using this diagram. So, no. Only 3 forces acting on it. There is no such thing as pushing force. It just slides up. And only 3 forces should belong to that diagram. Only 3. So this blue thing is a fiction. It doesn't exist. So total work should include three terms. The work done by normal force equals 0. The work done by gravity plus the work done by friction. So the work done by gravity is equal to mg y initial minus y final. And plus the work done by friction, it's always equal to -1 because of the cosine of 180 degrees times the magnitude of the frictional force, which equals to the coefficient of kinetic friction times the normal force. And normal force equals mg. No. It equals to mg tangent. No. Mg sine. No. Mg cosine of theta. So that's the normal force. That's the frictional force. And if you multiply by the distance traveled, well, in this situation, 5 meters, yeah, I can write a number. That's going to be the work done by friction. Now, of course, if we use our general agreement and we choose the 0 level at the lowest position of this object, the final height will be equal to what number? 3. Because it's 3 meters above. So initial is 0, final equals 3. That's it. You can now solve it for what we're looking for. So that's initial speed. We know everything. We know everything. The coefficient, the angle. We actually don't need the mass again. Gravity is 10. Done. See? We just have to write the law, and then we have to kind of uncover the meaning of each term of that law. Kinetic energy, okay, it's mv squared over 2. Work, well, depending on what force does it do, it's going to be one expression or another. And it's like solving a puzzle, basically. Sudoku. In this problem, the difference is we are, yes? Why? Well, you have to compare two pictures. This is the picture of what is happening in the problem, and this is a picture of what's not. So here, the box has been pushed just here at the bottom. See? This is that. And this is this. See the difference? This situation is physically equivalent to a situation when we have a string attached. So here we have only 3 forces. Here we have 4 forces in general. Now, in this situation, the coefficient of friction is not 0, which means let's use work kinetic energy theorem. Instead of using law of conservation of mechanical energy, we used just 5 minutes ago. So kinetic final minus kinetic initial equals, well, Still only three forces. So the work done by gravity, plus the work done by friction, plus the work done by normal. Well, we can just cross it out. It's always zero. That's supposed to be equal to mv final squared over 2 minus 0, because it starts from rest. And that's supposed to be equal to mg. So again, if we set the zero level here, that's going to be y initial, which is 20. That's going to be y final, which is 0. So, but remember, that's initial minus final for the work done by gravity. So 20 minus 0 plus work done by friction, cosine of 180. The magnitude of the force of friction, which is equal to the coefficient times the normal force. And here, we don't need to calculate it, it's given. So we assume that during this motion, the normal force always had the same magnitude, which is 15,000 newtons. And times distance traveled. And again, it changes. We don't have to. We could have probably, if we knew the radius of each arc, but it's just a given number. The distance traveled is 80 meters from point A to point B. So this total distance is 80 meters. And that's it. This number also is a given value, 0.33. The mass is 2,000 kilograms, 10. Nothing left to do. So the straightforward application of the law immediately tells us everything. Moving on. Okay, if you have a question, please raise your hand. Moving on. So this is a copy of the slide which you saw when we just started this topic. This is what's left. So we have covered everything what was inside, everything related to the energy. Well, let's start from solving a very typical problem. We call it a collision. Yeah? Collisions happen everywhere. I just had a collision recently. It wasn't my fault, so I'm not paying for that. Another guy. But still, a very similar situation. Ball hits the wall, bounces back. So please read, because I'm going to ask everybody a question. 100-gram ball flies horizontally. Everything happens so fast, so gravity practically doesn't affect its motion. And at first it was traveling to the left. Speed was 10 meters per second. It bounces back. You see, it says an ideal collision, which means no loss of energy at all. It wasn't spinning. So after the collision, it travels in exactly opposite direction at exactly the same speed. That's what it means. And question to everyone, please calculate the magnitude of the acceleration of this ball during this collision. So again, this is the initial velocity. The magnitude of the initial velocity is equal to 10 meters per second. It bounces back. An ideal collision means the velocity, final velocity, just after the collision, has exactly the same magnitude. and opposite direction to the initial one. So the magnitude of the final velocity is again 10 meters per second. The collision lasts a fraction of a second, 1/100th of a second. So what is the magnitude of the acceleration of the ball? This I can close. This I can close. Put some pressure. So on the blackboard, you can also supposed to see the statistics for the exam. I haven't checked it yet. Probably on Monday, I'll say a couple of words in general. Well, of course, we understand if we answer this question correctly, we solve the problem correctly. If we need to calculate the magnitude of the force acting from the ball on the wall. Yeah. When the ball is touching the wall, it exerts the force on the wall. That's the force which we call the ball, the wall. And this is what we're looking for. But now we know that according to the third Newton's law, there is also a force acting from the wall on the ball. The force wall ball, which must have exactly the same magnitude. And the free body diagram for the ball has only this force. The rest is not important. So that's supposed to be equal to m times a. That's supposed to be equal to 0.1 in kilograms. So as soon as we know the acceleration, done. Let's see what you said. Close this. So let's solve it. Oops. Okay. Still in there. So acceleration is equal to what? What is the definition of acceleration? Anyone? Exactly. So final velocity minus initial velocity divided by time. So this is final velocity, the arrow which points to the right and has magnitude of 10 minus the initial velocity, which is another arrow. It points to the left, but it has the same magnitude, divided by 0.01. If you want to calculate the magnitude of acceleration, we just need to calculate the magnitude of this. How do we subtract vectors? Well, we change subtraction to addition. Instead of subtracting a vector, we're adding the opposite. So now we have one long vector so the magnitude equals any questions? Well, but for my purpose, that's an illustration of how we can rewrite the Newton's law. You see, F equals m times a, but a equals velocity final minus initial velocity initial over time. So, hence, we don't like fractions. We can multiply everything by time, and we don't like differences, well, parentheses. So this is how we can rewrite the Newton's law. It's the same Newton's law. It's just written slightly differently. But turns out these variables, these combinations of variables, well, kind of handy. So in physics, if something gets handy, first we name it, and then usually we assign a letter. So this is what we call the impulse of the force. This is what we call the momentum of an object. So it turns out the Newton's second law also can be written like that. This simple expression has a slightly different name. We call it impulse momentum theorem. It's proved. And there's even shorter version of that. It can be any shorter. But this is basically the Newton's second law, just, hidden inside it. The momentum describes, well, this is an official definition of momentum. First of all, in general, it is a vector, because velocity is a vector. So mass is never negative. So this physical quantity momentum always points in the direction of velocity. Velocity points to the right, momentum points to the right. Velocity points to the left, momentum points to the left. And in our problem, this arrow should represent the initial momentum. This arrow should represent the final momentum. And the change in the momentum, delta p, is this long arrow, is equal to the impulse transferred by the wall to the ball. The impulse getting impulse of the force. Well, of course, I've got a better slide. This is the Newton's second law. Yeah. And because we know a lot of things about acceleration and velocity, we can transfer that knowledge directly to what we know about force and momentum. For example, if we go back in time, we've seen this picture. If we have a graph for acceleration as a function of time, the area covered by the graph is equal to the change in the velocity. But if we multiply everything by m, by mass, ma gives net force, and now mv gives momentum, and net force times time of action, by definition, equals the impulse. So now the graph, the area covered by the graph, will be equal to the change in the momentum or the impulse transferred by the force. But of course, here we will use only one case of one-dimensional motion. Otherwise, the graph would have been multidimensional. So in a one-dimensional situation, when force and momentum and velocity might point only, well, left or right, in this situation, we can use this graph, and depending on direction, each component of this equation could be positive or negative. You know, if momentum points to the right, so it has a positive component. To the left, negative. Same force, same impulse. So again, we could have used components. This might ball hitting the wall. The initial momentum and the magnitude of the initial momentum is equal to 100 grams times 10, 1 watt. There is no special unit for that. Mass times velocity means kilogram times a meter over a second. That's the unit of momentum. The final momentum looks like this. Its magnitude is the same. But what about components? Well, normally we choose positive x direction to the right. So the x component of the initial momentum, that's Ni. The x component of the initial momentum should be equal to -1. And the x component of the final momentum should be equal to 1. And the change in the momentum should be equal to final minus initial, which is 1 minus -1, 2. Now, this slide is not new. It just combines, again, the same information we just said. The Newton's second law, the impulse momentum theorem. We can use it differently. For example, we can solve it and we can calculate the final momentum if we know the initial and if we know the impulse transferred. How can we get the impulse transferred? Well, two options. Number one, we can use a graph if the graph is provided. The area covered by this graph is equal to this J. Another option, if we know the external force, well, on average, it might change in time, but the average is important. In that case, and if we know how much time it was acting, this product gives the impulse. Impulse plus initial momentum gives the final momentum. Another possible application of the same theorem. Let's say the impulse is 0. What does it mean? The net force is 0. What does it mean? It means no forces are acting at all, or they all cancel each other out. Now you see it says for any system. System, what is its system? What is a system? What is a system? Wherever we want to. It could have been one object, 10 objects together. If we choose the system, we always divide the whole universe into two parts, inside the system and outside. The internal forces never part of this because they don't change the motion of the system overall. Only external forces important. So if they zero or cancel each other out, that's it. This final momentum should be equal to this initial momentum. If something doesn't change, if something stays the same, how do we usually call it? Conservation. So this is the law of conservation of momentum. Well, strictly speaking, linear momentum. Everything is linear. Yeah, it's a vector. So if the net external force acting on the system is 0, the momentum of the system doesn't change. We'll apply this law to solve several problems. Well, we should say, what is the momentum of a system? If it's one object, well, it's mv. What if it's two objects? Well, each object has its own momentum. If we add them up, that's going to be momentum of the system. Okay, so that's the last slide. if we have two objects involved in a collision, the law of conservation of linear momentum looks like this. That's it. And now you can solve so many homework problems. Have a nice weekend. Yes? I don't. I don't know about you. We don't have to make any classes up. There are no classes to make up.
Oh, are we supposed to take the homework for week 2?
This is yours. Keep it.
Okay, cool, thanks. I have a question about the definition of what this means.
Yes.
Sorry.
Yep.
I checked the syllabus. It says, on the syllabus it said that the homework usually due 10 p.m. So, that's different from what the website says.
Can you show me? Blackboard?
No. You hand out it's also on the Blackboard, and it's also on the hard copy you held. I can try to.
Can't hear you.
Okay, then we take attendance today.
Yes. I don't know. Excuse me, where is the attendance sheet? Sure. There is no submission policy. If you want to make sure your grade is correct, you have to find me when I doing my office hours, and I will take a look at it. Okay, so I don't see any contradiction. These assignments usually do the 10 p.m. on the due dates. So the due date was February 25th. And it was.
But the actual due time is but 6 p.m.
Yeah, but it says usually.
Okay, all right.
So it doesn't say that it has to be 10 p.m.
Okay.
So why do you ask me this question?
It's because I follow the
And how many problems? Well, you have to send me an email.
Okay.
And I will check on this situation.
Okay. Okay, cool. Thanks.
I don't know yet, but it's supposed to be on Blackboard. There should be a way to see it. And on Monday, I will show it as well, just in case. On Monday, not now. I don't know it yet.
class graded based on like a curve to the average, or is it just graded based off of what grade you got on the exam?
Well, more the latter than the first one.
Okay. Sounds good. Thank you.
I just keep it like exactly like it is.
I think I think I write down. I have write down my work. Equation that I use. Then
But how did you solve them? You can't solve these equations in your head. You have to actually do something about it.
Yes, I have done it like here or somewhere, and then I think it's too much. Like
Where?
I don't know. It's like around here, and then now you erase the work because it's too much. Like there's too much number.
So this is a teachable moment. Don't erase things.
Okay. Yes, I really wrote down a lot, and then I
Why? Why would you erase it? It's easier
I think
work.
it's.
We don't grade results. We grade work.
I think that's the work because I have two equations, and then the
That's
answer.
not the work. It's only beginning of the work. How would I know that?
Because I'm
you just
afraid.
didn't remember that. How would I know that?
No, that's not
Well,
true.
but how can I know that?
Because I'm afraid that it's too like you can see it's too troublesome to grade this.
No, not on the contrary. You lost the point because of this.
Yeah, but I really know the answer. I really know the work.
And how can
I
can you prove it?
I can show you now. Like I can do it now.